Hey, this is part two of accumulation and Riemann sums and definite integrals. We're going to be exploring trapezoidal approximations and their advantage over Riemann sums and rectangles. Now, again, remember, trapezoids are figures with one pair of parallel sides, and it has a base. And here is the formula for the area of trapezoid. And you could see in this picture to the right that we have trapezoids. The h is the height. We have base 1, base 2. And as you notice that these can be good approximations because there's very little under and over on each of the trapezoids. So let's do trapezoids to approximate the answer to example 1. So example 1 reads, an amusement park opens its doors at 9 a.m. The rate that people enter the park is given by p prime of t in thousands of people per hour. The values are listed above. Use trapezoidal approximation with 3 subintervals to indicated in the table to estimate the total number of people that entered the park from 9 to 7. So 7 would be 10 hours after the park opened. So we're not going to use this value over here. Okay, so when we do these, if you picture the trapezoid, right? So this value is going to be your base 1. This is your base 2. And the height is going to be this value here, which is going to be 2 minus 0. So kind of over here drawn on the right, very poorly, of course, is what the picture will look like. Something like that. And so let's calculate this value. So my first trapezoid is going to be, one of the bases is 7, the other bases is 11. And again, we have the base 1 plus base 2, which is going to be 7 and 11, divided by 2, times the height, which is the difference between t, so 2 minus 0. So this is going to give us 18 for the first trapezoid. The second trapezoid here is going to be the height at 2 plus the height at 5. I'm sorry, I said height. It's going to be base, the first base, which is going to be 11 units high. This base, which is going to be 8 units high, divided by 2, and then the height is going to be this distance, which is 3. So we're going to get 11 plus 8, which is 19, divided by 2, and then times 3. And then our final trapezoid is going to be this. So it's going to be this is the base at 5, which has a height of 8, the base at 10, which has a height of 4, and the height of the trapezoid is 5. So this is going to equal 30. And then if we add up all of these values together, we should get that it is 76.5. And again, and this is in thousands of people. So it's going to be 76,500 people. Okay, so this is what we were approximating in example 1. We were approximating the area from 0 to 10 under the function. Two little things. This is more of a vocabulary. When we're adding together values or subtracting values together, then you use the word total because you're, adding a bunch of things together, or you could be subtracting a bunch of things. So that is the total. If you're adding and subtracting, it's called the net change. It's not the total change, it's the net change. So interpreting this integral, it says it's the amount of money in the bank is changing at a rate of a prime of t, where a is measured in dollars per day and t is the number of days since January 1st. Interpret in context. So if this is money in a bank, there are values that are going to be added in and subtracted. So when you get paid, your money goes in. When you make a debit payment or pull out cash, the value decreases. So we are adding and subtracting values. So this is going to be the net change. So it's the net change in amount of money in the bank account was negative $853 from t equals 0 to t equals 10 days after January 1st. And again, there's another way to say this. You could say from January 1st to January 10th, right? Because that would be 10 days after, but we just leave it like that so there's no mistakes made. Example 3, the rate in dollars per day that Mr. Love spends money can be modeled by the function. where T is the number of days since January 1st. Interpret the following context. So, in the first 10 days of January, Mr. Love has spent a total amount of $2,457. And again, because you're spending every day, you're just adding up the amount you spend. So this is going to be a total change. Okay, moving on to the next idea. It's the idea of under and over approximations. So basically, when you're using Riemann sums, when you're adding up rectangles, if the function is increasing and you're doing left-hand Riemann sums, your approximation is always under what the actual value is. And if the function is decreasing while using left Riemann sums, your estimation is over the actual value. And then when you're doing right-handed Riemann sums, if the function's increasing, you are overestimating the value. And if the function is decreasing, you are underestimating the value. And this can be kind of easy to see. I guess we'll just use this little triangle or this little line to say. So look at the function there is increasing. If I'm going to use a left Riemann sum, my rectangle is going to be smaller than the value. There's all this missing area, no matter what you do.
Like and subscribe.
Okay, thanks, Ronan. Love you, buddy. So it's increasing, so a left-handed Riemann sum is always going to be under. And if you do a right-handed Riemann sum, you're always going to have a little bit over, like this area here. No matter where you go, there's always going to be a little bit over. And the opposite is true when you are decreasing, right? If you're decreasing and you're doing a left-handed Riemann sum, you're always going to have a little bit over the curve. And if you do a right-handed Riemann sum, you're always going to have a little bit under the curve. So that's a kind of an easy way to conceptualize this. Now, it's a little bit harder to see under and over with trapezoids and midpoints, especially with midpoints. I would just memorize this. You can maybe look up a video of why, but it's a little bit harder to see. But trapezoids is fairly easy to understand, right? And it's about concavity. So if you are concave up, your trapezoids are gonna be over estimations. So let's draw concave up and see. So if you do this, you're gonna have a little bit, I guess it's kind of hard to tell right there, but when you go, there's gonna be a slight bit over with concave up. So trapezoids, if it's concave up, you're overestimating. And if you're concave down, you are underestimating, right? Because you go here and it's going to be underneath. Because again, when you're concave down, this value is higher than this value. So it's going to be slightly under. But when you're concave up, your right-handed value is going to be slightly above the left value. So that's why it's an overestimation. Okay, this question is a little bit difficult, but okay, so we have a twice differentiable function here on the interval 2 to 7. So let L of S, R of S, and T of S represent left Riemann, right Riemann, and trapezoidal approximations. And then it says, which of the following inequalities is true? So basically you have these options. And remember, this right here is the actual area. I guess we could say the exact area. So let's look at left and right Riemann sums. So this is decreasing. So my left Riemann sums are always going to be an over approximation. So my left Riemann sum is an over approximation. My right Riemann sums are going to be an under approximation. If we look at trapezoids, this one is going to be an over approximation also. And you can come back here to verify. So you are concave up, so you're going to be an over. Okay, so automatically we know that we have the right Riemann sums at the bottom because that is going to be an underestimation of the actual area. And then you have the actual area here. So like this value is always going to be bigger than this value. Why? Because right Riemann sums are going to be under the actual value. Now, these are both over. So which one kind of overestimates more? And you can kind of do this conceptually. So we need to see which one of these gives me more error. And let's just pick 4 to 5 right here. So if I go from 4 and go over and down. So look at this. That is my how much I overestimate it by. And if I compare it to a trapezoid, it is going to be overestimation, but it's like a small overestimation. So I would say that this overestimates more than the trapezoid. And so there is our pecking order, which we can see that D is the right answer. Example 5. For t from 0 to 6 seconds, a large glass is being filled with water at a rate of W prime of t, measured in ounces per second. And again, we can see those units here. The selected values are given in the table. Okay, approximate the area using left Riemann sums with 3 subintervals. So here's kind of a picture. And again, since we're using left Riemann sums, this left value is going to determine the height. So with the first rectangle, the height is going to be at value 1. With this second rectangle, we're using the left side to determine the height, so the value 2. And then with the last rectangle, we're using the value of 4 to determine the height. Okay, so W prime of 1 times 2 minus 1. Again, W prime of 1 is this value, which in this case is 2.3. So this is 2.3 times 1. Plus, we have our second rectangle, which is going to be the value at 2 times the width of the rectangle, which in this case is going to be 4 minus 2. So the height at 2 is 1.7 times 2. And then finally, our last rectangle is going to be a height at 4. And then the width is 5 minus 4. And the value at 4 is 1.2 times 1. So if you multiply all these together, you get that this is approximately 6.9 ounces. And again, units, we have ounces per second times seconds. So my final unit is in ounces when I do the area under the curve. Now, part B, using correct units, interpret the meaning and context of the problem. So basically, since it was a glass of water, we would say a glass of water was filled with 6.9 ounces of water from t equals 1 to t equals 5 seconds. Part C, is your answer from part A an over or under approximation? Well, look at the function. The function is decreasing, and we're using left Riemann sums. So without going back to the table, if you are decreasing and you are using left Riemann sums, you are going to be an overestimate because you're going to get this little bit of extra. So the official answer is overestimate because W prime of t is decreasing. Last two examples. Example 6, you have from 0 to 5 seconds, a particle is moving along a horizontal axis with the velocity v of t measured in meters per second. The graph is shown above. Interpret the following. So notice that we do have a positive change and a negative change. So if you recall in the last video, this is going to be a positive area and this is a negative area because this one's under the x-axis, so that's considered a negative area. If you're above the x-axis, you're a positive area. So this is going to be a net change. So from 0 to 5, the net change is 6.25. But it's the net change in what? So if you remember area, we're going to take this unit times this unit. So we're in meters per second for the y-axis, but you got to times it by the seconds. So this is going to be changes in meters. So the first one is the net change in distance is 6.25 meters from t equals 0 to t equals 5. That's the correct interpretation. Part B, now notice how there's an absolute value here. So this right here is a little tricky because this is not negative anymore. So this area is going to be added to this area because with absolute value, you only keep the positive. So this is going to be total distance traveled. So you would say the total distance traveled is 12.65 meters from t equals 0 to t equals 5. This one, we do have an extra unit outside. So this part right here is going to be in meters per second times seconds. And then the 1 over 5 is 1 over 5 seconds. This cancels out with this, and we're still in velocity. So this is the average velocity because we're in meters per second. So the average velocity from t equals 0 to t equals 5 is 1.25 meters a second. Okay, last question. Example 7. On a road trip, Mr. Hang decided to track his mileage during the trip. The efficiency of his car is modeled by the differentiable function m of g, measured in miles per gallon, where g is the number of gallons of gas he has used on the trip. The selected values are given on the table. It is known that m is decreasing between 2 and 12. Well, obviously, if you're using gallons of gas, like you're only going to be using them. Okay, so part A, estimate the value from 2 to 12 of m of g dg using a right Riemann sum and 3 subintervals. So I'm not going to draw this anymore. We will explain it though, of course. Okay, so using 3 subintervals, so it looks like here's going to be a rectangle. There's my 1, there's my 2, and then it's my 3. But since we're using right Riemann sums, we're going to use this value for the height. When we do the first rectangle, we're going to use 28 for the height. So the height of my first rectangle is 28 times the width, which is going to be 2 minus 5, which is 3, plus the next rectangle is here. We're going to use a height of 26 because we're using the right side. And the width of the rectangle is going to be 10 minus 5. So this would be 26, and this is 5. And then the final rectangle is going to be here. We're going to use this value. We're going to use m of 12 to decide the height, which is going to be 25. And again, times the width, which is going to be 10 minus 12. I'm sorry, 12 minus 10. So we have 84 plus 130 plus 50. And that should be 264. And again, we need to figure out what units we're in. So if we're in miles per gallon times gallons, it looks like my units are going to be in miles. Now, are we in under or overestimation? Explain your reasoning. So it does tell us that we are decreasing. So if we're using right Riemann sums, we're going to be underestimating the value because this is used to determine the height, right? So we're going to be leaving a little bit above the rectangle as an error. So I put underestimate because m of g is decreasing from 2 to 12. Using correct units, interpret the meaning of this integral using context of the problems. Let's kind of look. This right here, this value is going to be in miles per gallon times gallon. And this 1 over 10 is going to be in gallons. So if these cancel, look at what our units are. They're still in miles per gallon. So what this is the average miles per gallon on the trip from 2 to 12. So that's the formal explanation, the average miles per gallon during the trip from the number of gallons g equals 2 to g equals 12. And that is it for part 2.